So this is a continuation of a talk I gave a couple of years ago. So it's a similar language, a similar semantics, but a different problem. So let's look at the problem. The problem is how to give a differentiable programming language a good operational semantics. And what does it mean to be good? Well, it should be adequate. It should correspond to some natural denotational semantics. That's a standard thing to ask for. It should be structural. So I want to give an operational semantics that directly gives the operational meaning of the program. I don't want to give some complicated implementation of some kind and say that's the operational semantics, because it's not. It should treat differentiation in a natural way, the kind of thing you'd expect knowing about differentiation, whatever that means. And it should be in the spirit of some current implementation method. The last two criteria could have been contradictory, but luckily they're not. Okay. So here's the language. And the language is nothing really except for the very last line. So it's a first order language with recursive definitions, so you get while loops, but much more. And its type system is very impoverished. It's just got finite products of the reals as its types. But that's all that most automatic differentiation uses anyway. But it's still embarrassing as a PL person. One would like much more. The main thing is this reverse differentiation or vector Jacobian operation in red at the bottom of the screen. In the paper, that's done in terms of the differential function, but I thought just for fun, to give myself some fun preparing a lecture, I'd use the vector Jacobian. Anyway, it's a thing that everyone knows is a concrete thing. It's easy to define. But it's not so conceptually pleasant as the reverse differential. But the reverse differential is nothing more than the function you get by using the vector Jacobian as a function, applying it to vectors. Okay, so I won't explain yet what all these bits and pieces are, but it'll come out when we get to it. So just a brief resume of why might we want this? Well, of course, if you want to do deep learning, then you have to do gradient descent. If you're going to do gradient descent, you have to measure gradients. And so that had better be a gradient construction in your programming language. This is gradient descent. You've probably all seen that lots of times. There's a slope. You want to go down it. So you're at some point x. You want to move to some point x prime by going down the slope. A r amount, that's called the learning ratio. You have to fix that. Times the slope of call this the loss function. You're trying to minimize loss, times the gradient of the loss function at x, dl by dx. This is a very trivial gradient descent program. There's a whole plethora of more and more complex ones, but this kind of gives the basic idea. And of course, there's not one parameter. As someone said, there could even be billions of parameters. But let's look at the case when a billion is equals 2. So here we have a function, a little countryside, and we want to go down to the bottom of the valley. So we've got the loss function now has two arguments, x and y. So we can go down as fast as possible in the x direction. X prime equals x minus r dl by dx. That's just like before, but only in the x direction. And the same thing in the y direction. We put them together, we get x prime y prime equals xy minus r times the pair of the partial differentials, which is nothing else but the gradient. And you can generalize that yourself clearly and to n dimensions. And it's not so hard to show. It's not just you're going down as fast as possible in each of the directions, x prime, the x and y directions. This is as fast as possible as you can go down the slope. Any other way of going down isn't so fast. It's a little theorem. Okay. So what would we want to have in the language to do that kind of thing? We naturally have some kind of gradient construction. Gradient of some function at given x returns L, where L some term, and we differentiate that at x. So this way of speaking is very natural, but complete nonsense. Why is it complete nonsense? Because L isn't a function, it's a term of our language. And over on the right-hand side, it looks like I'm taking the derivative of some function, but it's not. It's like a term, right? But somehow this is okay, because if we were thinking carefully, it wouldn't be the L, but it's a denotation that we're taking. But on the other hand, this is the kind of syntax that we're going to have to work with. So gradient. So as we generalize from these simple gradients, we get to Jacobians. So I'll just do that in a couple of steps. So So L is L is a function that takes reals to reals. So we could take, say, pairs of reals to reals and have a function L of xy, and do this gradient here. And intuitively, that would be, it's basically just the thing we had in the gradient descent, but written with terms rather than, written illegally with terms rather than legally with functions. So that's a gradient construction, and it's a function L which depends on a pair of reals, but in general, we'd want it to depend on an arbitrary type of the language. Arbitrary type of language is essentially a product of reals. So this is just an n-ary function. It's not exactly an n-ary function because of this fact that you can have brackets and parentheses, but so you could have real squared cross reals rather than real cubed. But apart from that trivial thing, it is okay. How about when you have three inputs and two outputs? So you've got say x, y, z coming in and n and m going out. Then we could differentiate. We can take the gradient of n at x, y, z and the gradient of m at x, y, z and stack one on top of the other, and that's the well-known Jacobian. You have to be a bit careful because things go backwards. So if you look at nm as a function of three arguments takes three things to two things, but the Jacobian is 2 times 3. And this switch is an important one to keep in your mind. You don't usually want the Jacobian because it's just too big, so you do either you do the vector Jacobian or the Jacobian vector. And for going backwards, we want the vector Jacobian. So here we'll do the matrix multiplication on the left. We'll take the vector ZW and multiply it on the left. And that'll give us, so that's 2 and then 2 by 3, so that'll give us as a ternary thing. So we've gone backwards because that function, nm function, goes from 3 to 2, but now we started with 2, namely ZW, and gone to 3. Okay, so this is why it's reverse differentiation. I mean, you could do forward 2, but this is the generalization of gradients. And the general vector Jacobian products, we just have so that's going, instead of going from 3 to 2, just go from one type T to another type U in general. And from a programming language point of view, that's what you want. You want a differentiation construct which is polymorphic over types. You don't want to say it's for this type or that type only, but it should just be polymorphic here for all types, T and U, even in such an impoverished language. Oh, that's going backwards. I want to go forwards in the talk and backwards. Anyway, so the mini language, here's the typing rules, and I just want them for two purposes, but they're perfectly standard. You've got two kinds of variables, ordinary ones and function ones, appropriate notion of environment for each, an appropriate notion of judgments, terms of type T, and Booleans are another class. I won't say much about Booleans, but you just do fairly reasonable things for them. Here's the typing rules for them. What point do I want to make? The operations are given types. Examples could be, say, dot product or matrix multiplication or Einstein products, all kinds of things. Just enough reals. I'll have predicates like less than over the reals, but notice there's a little dot over that less than. That's there for a reason. But there's the vector Jacobian product. So it's just what we say. So n goes from T to U, so that's, I don't have that thing on me. That's that up there. So that you should evaluate it to x, so x should be of type T, and you come from the right, namely the y is type U, and you get out a type T going backwards. So the function xtn goes from T to U, and the vector Jacobian pulls backwards and ends you up with a U. Okay? The reason I put the function definitions up there is that if you look at the bit in red, that ensures that the only free variable in the body of the function is x. So we're not allowing free global variables in recursive function definitions. That's because I couldn't prove a result by being more general, not because there's any good point about it. But I think I can now, but not in time for the conference. Okay, so this is just to show you, like it's perfectly easy to write gradient descent in this language. So we want to learn some function from reals to reals, and to do that, we'll use exactly one example for AB, and we'll have a model with one parameter as opposed to billions, And so given that data, you can make a loss function, which is the loss between what the untrained model says and what the actual thing is. That gives you a loss function, and you can, as long as your loss is still a bit too big, less than, until it's less than C. Well, if it's small enough, it's less than C, you output W. Otherwise, you descend, and this descend formula is just exactly what I wrote on the board, but in programming notation instead. So I'm just saying that's really a little loop, of course, written recursively. And but this language, trivial as it is good enough to write all kinds of things. Very clumsily, very unpleasantly, but you can do it. Okay. Okay, so how should we do differentiation? How should we evaluate it? What kind of structural operational semantics should we have? Well, let's try and differentiate some things. So some things are easy. And I'm just going to work with, let's just try and do a gradient. So I want the gradient of f of g of x, where f and g are given operations of language. So we should just take the gradient of f at g of x, g of v, sorry, v is a value in the programming language, times the gradient of g at v. That's just the usual formula, it's the usual chain rule for, I've used 10 minutes. Oh. That's interesting. Okay, so what I will say at a higher level in that case is that the chain rule turns into a very simple source code translation. And I was going to go through it more gently, but I won't. Yeah, so that's that. So how about if you want to do control flow? That's more interesting. What's the gradient of a conditional? The gradient of if something, then something A, then else B is naturally going to be if the first thing, then the gradient of the second, else the gradient of B. Why is that true? Because suppose that x is 5, then the left-hand side is equal to the left, the true branch at 5. That argument is a false argument, but it's the one people think of, so we expect that. Another way to do it is tracing. So that's the source code transformation method. The tracing method is, you see that x is true, so you symbolically evaluate the expression if blah, blah, blah to x squared. So this twiddly thing means symbolic evaluation. And then you know how to take the gradient of this thing because you get rid of the control thing. So that's what you do, and that's the kind of, so we're going to do this tracing method. This is nested differentiation. How would we do nested differentiation? And it turns out we need to symbolically evaluate not only the body of gradients, but the gradients themselves. Because if I'm going to, I won't go through the details, but if I'm going to evaluate gradient of y plus the gradient of something, then I'll need to symbolically evaluate y plus the gradient of something in order to do differentiation. So I'll need to symbolically evaluate that. So, and eventually that turns into, when I do the usual tracing for the conditional, I get to needing to do gradient sub y of x cross x squared. So I need to evaluate the gradients at symbolic values. So I'm going to allow free variables and values in order to achieve that. Okay, so here's the operational semantics. So we allow variables in values. That's the difference from the usual thing. And because we allow variables in values, we're going to have to do everything relative to environment when we're doing the symbolic stuff. So I just uniformly make everything relative to environment everywhere. And I won't bother about closures. So there's two relations, ordinary evaluation and symbolic evaluation. And what do we symbolically evaluate to? Well, we symbolically evaluate to terms of the language with no control flow. And these are all just listed there. Notice that this is very far from being an anormal form in any sense, which is what you want for efficient differentiation. But I'm not trying to do efficient differentiation. I'm trying to do natural differentiation, which is certainly not efficient, and vice versa. So these are just ordinary rules that you've seen a million times, except for the vector Jacobian products. The vector Jacobian product, you just punt. You say to differentiate a vector Jacobian product, you just symbolically evaluate it. And that'll give you an ordinary term, and then you evaluate that. So the question is, how do we do symbolic evaluation? So in some sense, it's pretty trivial. You symbolically evaluate x to x. You symbolically evaluate up of v to up of v. I should say in parentheses, this is the Fleisen method. So there's some mechanism of evaluation context, but okay. And conditionals is what I just said. Local definitions, actually I don't want to go through it too much, let's see. Vector Jacobian products, this is the critical one. You symbolically evaluate the body of the vector Jacobian product, so you get C. And now this C is a very simple thing, so I can a source code, do a translation, a symbolic differentiation on that. So I've got rid of all the control structure. So I need to define this thing J, and that's just a syntactic definition, absolutely no time to look at that. And how much time do I have now? 4 minutes. 4 minutes, oh great, okay. So this is differentiation conditional. So there's the rule. These are real mathematics now. And so the equation is what you might hope for. The equation is false. Because you take this little example, if h is if 0, then minus 1, minus x else x. That's a definition of the identity function. So its derivative anywhere is 1. But if I use the rule, I'm going to get if 0x, then minus 1 else 1. So that's going to think that the derivative at 0 is minus 1, which it isn't, it's 1. So what's gone wrong? Tracing also doesn't work for a similar reason. What's gone wrong is, although the first branch of the conditional was equal to the whole conditional at a single argument, it isn't equal to it in a neighborhood. You have to be able to wiggle around to define different derivatives. So that's the problem. So we're going to have to change predicates so that they're nicer. For example, we have a dotty version of the less than one, which is okay. You see, if you think about when x is less than y, if you're above the diagonal, then you can be in a little neighborhood around there and still keep away from the diagonal, and equally below the diagonal. But if you're on the diagonal, any neighborhood is going to get you into ambiguous territory. So you have to keep away from the diagonal. Okay, so this is technology that I'm simply not going to talk about. We need to be able to differentiate, but we've got nested differentiation, so we need to differentiate as many times as we like. So functions we can differentiate as many times as we like are called smooth. So these are just the definitions for that. And then the proposition is that if f and g are smooth, well, here it's just continuously differential, but it holds for smooth too. If they're smooth or whatever, then their conditional is smooth, as long as this b satisfies that extra condition of keeping away from the diagonal. And then the general rule is now true for that. So if you have the right conditions, things work. That's the semantics of the language. What am I going to say? I probably just want to get straight on to the theorems. So yeah, I think, and then make some final point. So it turns out there's basically four natural theorems you want to prove. First of all, you want to prove that symbolic differentiation is correct. So that just says the meaning of a VJAC and the meaning of what you get by doing the symbolic differentiation of it, they're the same as long as you're doing it to a trace term. And that's just a nasty induction. You want to say the operational semantics is correct. If you value it to value, then the term and the value are the same thing. But for symbolic differentiation, you want to say something a bit stronger. You want to say not only if m evaluates to a trace term, not only do they have the same meaning at rho, or rather denotation of rho, but they do in a little wiggly neighborhood around it. So this is just the general thing you want to be true that includes the particular difficulty with the conditionals. So you want that to be true in the neighborhood of the environment. I'm not going to explain anything about why it. So then the final thing, you need that for correctness, but for completeness you don't. Completeness is the converse, that if the denotational semantics predicts a certain value, the operational semantics will give the value. And for the symbolic thing, it says that if the denotational semantics predicts there should be a value, then you'll evaluate to some trace term. And there's a cute lemma, 2 follows from 1, because you have this operational interpolation lemma, saying that if m evaluates to a value, that's true if and only if there's some trace term that you could trace m to, which then evaluates to the same value. So you can interpolate a trace term between a term and its value. And in some sense, that's the end of the talk. And there's many, many continuations, but one, just to give an example of problem, How about efficiency? There's absolutely no attention to efficiency. What would it mean to be efficient here? Well, I think it'd be nice to have a verified efficient implementation. Well, I think it's the kind of thing you'd have to do. You wouldn't work directly in the language. You'd invent an intermediate language. I don't know what, it's not obvious what an intermediate language with nested differentials should be. Anyway, you'd invent it, you give a verified compiler to it, and you give a traced mechanism for the intermediate language. When people do tracing, and they're tracing iterations, you don't trace all the way through the body. You only trace at breakpoints, which is at the beginning of the body. So you want to trace evaluation trace mechanism with breakpoints at recursive calls, and then show the mechanism correct. So that would be the kind of thing you'd have to do. Aditya Kanadi really, and I, but mainly Aditya sort of thought how that might go. So to do efficiency, you'd have to do a lot. It wouldn't be natural, but you would have this basic semantic background for the rest of the talk. So thanks a lot.
All right, so we have time for a few questions.
Yeah, thank you. You said that for if-then-else cases, you just take the gradient of the first case and the gradient of the second case, and then you copy the condition basically.
Yes.
But in your example, you had x is greater than 2, so this defines an open set, but 2 is at the boundary, and I think at the boundary this...
Oh, I should have put a dot over the greater than, sorry.
So I just wanted to ask if you have like a condition that defines a closed set, what happens at the boundary if the function there is not differentiable? Or...
Well, closed sets are horrible. With differentiation, you want open sets. It should have been greater than without a dot over it. It should have been the thing that keeps away from the boundary.
Ah, okay.
Yeah, I've no idea with what happens to closed sets. I imagine all hell breaks loose, but I don't know.
Okay, thank you.
Anyone here online? There's some other questions? No? Did you get any online? No. All right, then we'll thank Gordon again. Thank you.